Hi, I'm Ben-Yaakov. This presentation is entitled Current Amplifiers as Isolators. There is a disclaimer here that the devices shown in this presentation are for educational purposes only. There is no endorsement or recommendation implied. There are many applications in which we'd like to have a current source. There are different circuits and there are different applications. I'm showing here two areas of application. One in which we have a load and we like to pass a current, a constant current or a controlled current through the load. So in this case, we have a operational amplifier, a sense resistor, and the current through this resistor is controlled by the feedback. And assuming that the emitter current is the same as the collector current, which are very close within alpha, then by controlling the voltage here at the emitter, we control the current, and therefore this will be controlling the current of the load. But there is another range of application in which the purpose of the current source is not to pass a constant current or control current through a load, but rather to serve as sort of a translator or isolator between a voltage that is sensed and an output. For example, here we have a voltage which is sensed by this transconductance amplifier producing a current, and then this current is passing through the resistor referred to ground. So we're getting here on the resistor a voltage which is proportional to the input, because we have the input and the current is proportional to the input voltage, and then the voltage developed here is the current times the resistor. I'm talking about this type of application, and I'm going to show two examples which are sort of similar, but they are a bit different in the way they are implemented and the purpose. The first one is a current sense amplifier. This is a unit by Texas Instrument, INA 139 or 69. Originally, it was developed by Bear Brown as INA 138 many, many years ago. I think it's about 25 years ago. And then Bear Brown was acquired by Texas Instrument, and the unit was sort of changed a little bit and improved. And what it is a unit that is serving as current sensor. That is, we have a sense resistor here through which we are passing a current, and the voltage across this is then sensed by this amplifier, producing a current which is proportional to the voltage here, and then this current times the resistor is the voltage, and therefore the voltage here is proportional to the sensed current times the resistor here and the load, and divided by this 1 kilo. So this is this type of application in which we are not passing a constant current or a controlled current through a load, but rather using the current source in a different way as a buffer or isolator, I would say, between a measured value and an output. And how is this unit actually working? So if we have a current passing through this R sub S, it's developing a voltage, the current times the resistance. Without feedback, then this voltage will be imposed on the input of the amplifier, and therefore the voltage here at the output will go up. The polarity is plus and this plus. And as it goes up, the base current will build up, which will cause an emitter current and a collector current. So here we have it. This is the base current, collector current, emitter current, and they are, of course, closed within alpha. This is the beta over 1 plus beta. This is the current ratio between the collector current and the emitter current. So once we have a current here, this current is passing through this resistor, and at steady states, we know the input voltage to the amplifier will move to zero. That is, the feedback, negative feedback, assuming stability, etc., will cause this air voltage to approach zero. For that, the voltage across this 1K resistor has to be equal to V sub S, so that the sum of these will be zero. Here it is. And consequently, we have now a relationship between the voltage across the R sub S, the sense resistor, which is a function of the sense current, and the collector current. And therefore we find that the output will be equal to the sensed current times R sub S, R sub L, and divided by this 1K. This is from this relationship. The emitter current, the collector current are not equal, they are within alpha. And of course, there is some error here in this measurement if this is a BJT transistor. And the correction is this factor, which is basically alpha. And so this is the same expression as before. And this will be then the value of the sense current as obtained from the output current. Now we really don't know what is this element. Is this a simple BJT transistor? Is it a beefed up transistor with high beta? We really don't know. But if it is a regular or a conventional BJT transistor, then the error that you'd expect will be something like 0.5% to say 1%, depending on the gain of the transistor. Now the error specified by the manufacturer is a maximum of 2%. This is not very good because there are many applications in which you'd like to have a high precision measurement. Well, in some applications or in many applications, I should also say 2% will be okay. So in this 2%, you can actually absorb the error of this collector and emitter current difference, so which is like I've said 0.5%, 1%. So this sort of takes into account all of these. So this could be a regular transistor, although we really don't know what it is. Let me point out that one of the very nice feature of this device is the fact that the common mode voltage here of this amplifier could be higher than the power supply for the amplifier. Now the power supply could be between 2.7 volt and power supply 2.7 to 40 or 60 depending on the model type. And the common mode voltage could also be this range, but it's not dependent on the voltage of the power supply. That is, the power supply could be 5 volt, while here it could be like 40 volt. This is very powerful. So we have here sort of a buffering effect or isolation, if you might say, between the high voltage here and the amplifier, which is referred to ground here. Okay. Now, obviously, the power supply has to be, the voltage of the power supply has to be higher than the output. You cannot generate a output voltage which is higher than the power supply. Let's move now to another application in this area. And I'm showing now a circuit that is part of this patent. That's not the whole patent. There are many aspects to it. It is a patent by Paul Price and myself. And here is the circuit that I'm talking about. In this application, which is a bit different from the current sensing, although it has some common features, in this case, we are measuring the voltage of a cell in a battery. So there is an array here of cells, and we are measuring the voltage of one cell. Okay, this is an amplifier which is in a closed loop, and then we have a p-channel transistor, which then produces a current that is fed toward ground here. Okay, now without feedback, then the whole input voltage, V sub S, will be imposed on the input terminals of the operational amplifier. This will cause the voltage to go down. This is because of this polarity. Now the plus goes to the minus. And as the voltage of the gate goes down, then of course the transistor will start conducting, and there'll be a current building up until the voltage across this resistor is equal to the input voltage, such that the V sub E, the error voltage at the input to the amplifier, will approach again 0. So the condition is that voltage drop here, this is I times Rs, is equal to V sub S, and therefore we can relate the current here, which is the current here, to the input voltage, and therefore we can find that the input voltage will be the output voltage that is measured times this ratio of resistance. Now the nice thing about this configuration is that first of all, of course, we don't have the error because this is a MOSFET, and of course the source and drain current are very close, especially if it's a DC, of course. And then another feature is that the power supply for the amplifier is coming here from nearby cells. Okay, so this could be actually riding on a high voltage, 400, 800 volts, say, in an electrical vehicle battery. And so the voltage here could be as required by the amplifier, it could be a few volts. And then this voltage now is riding on the potential which is at this point of this particular cell. Now, in an application, you can have this circuit for each one of the cells and then get the output through the load resistor, having a multiplexer, which will be sampled by the controller. And then, of course, you can use this for balancing the cells. So, this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it'll be useful to you in the future. Thank you very much.